let's do a particle in a box problem. Okay. And remember what were the solutions to our psi for a particle in a box? Square root of 2 over L sine and pi x over L, right? Those are our psi's. Okay. You can let phi be equal to x times L minus x. Does that follow the same boundary condition as your psi? What's the boundary condition for this? Psi must be equal to 0 when x equals 0. Is phi equal to 0 when x equals 0? It is, right? So it obeys that boundary condition. Psi must also be equal to 0 when x equals L. Does phi obey that boundary condition? When x equals L, phi is also 0. Right? L minus x is 0, so phi is 0. So it obeys the same boundary condition. So we can use this as our trial function, our guess. Okay, let's pretend we didn't know that these are the solutions. And so let's verify that if we take this integral right here, it's going to be larger than E1. What's our E1 here? Is h squared over 8ml squared, right? So you need to take that integral right there. So what do? You take integral of x times L minus x h hat times x times operating on x times L minus x dx. That's your numerator, right? And this is your phi star, which is the same as just phi, and that's h hat phi, right? That's your numerator. What's our denominator? Integral of x times L minus x. Okay, and since this is real, we'll just square it, right? So it's phi star times phi dx. Is that greater than or equal to E1? You want to do that as homework? Bonus homework. Okay, let me get you started on that, and you can finish it yourself. You can do that easily with MathCAD. I'll allow you to use MathCAD. You don't have to. Let's see, where is MathCAD here? So if you take the integral of x times L minus x, okay, squared, this is the denominator, right? dx from x equals 0 to x equals L, what would that be? Will MathCAD be able to evaluate that for you? Evaluate symbolically. Oh, sorry. L minus x. Right there. That's L to the 5th over 30. Okay. And what's the other one we have to do? The numerator. So this is your denominator. What's your numerator? Integral of x times L minus x times, what's our Hamiltonian? We have to take the second derivative with respect to x of x times L minus x. Okay, what's our Hamiltonian again? H hat is negative h bar squared over 2m, right? Times the second derivative with respect to x. So we need that extra term out here, right? So this is just part of our numerator. So integrate from 0 to L, okay, dx. So I need to multiply this whole thing by negative h bar squared over 2 times the mass. What do you think this is going to be? There's the answer. Okay, so you got your numerator, you got your denominator. Can you finish this off? You should be able to, right? Verify that this is greater than E1, which is h squared over 8ml squared. Okay. Now that's not really very helpful to us because we don't have anything here that we can use to adjust the function. What you want to do is, okay, what you would want to do is you want to put parameters in your function that you can tweak, so that when you tweak your function, you can get that energy to go as low as you can. Right now, this is fixed. We have a fixed function, x times L minus x. There's nothing adjustable there. So how can you introduce something that's adjustable there? You can raise the function x times L minus x to the power n maybe, or some power, let's see. So for example, instead of writing it as x times L minus x, you can say x times L minus x raised to the power a. And then you just tweak that value for a. Okay, until you get as low an energy as you can. You may not get the exact solution because if it has no way of looking exactly like your psi, like square root of 2 over L sine pi x over L, you're not going to get the lowest possible energy. But you can get, for a given parameter, you can tweak it so you can get your lowest possible energy. So the variation method, okay, that's basically what the variation method's all about. You use a trial function that has adjustable parameters. Let's say your adjustable parameters are a, b, c, and so on. Like in the earlier example, let's say you just said x times L minus x, the whole thing raised to the power a, for example. Okay? Then your guess, which is going to be, remember, your guess is phi h hat phi in bracket notation over phi in bracket notation. That's your guess, right? Well, that's going to turn out to be, if you introduce a parameter in your expression, then let's say, then that's going to be a function of the parameters, a function of a, b, c, and so on. Okay, so that integral, you're not going to get a number for that integral. You get an expression of that integral that depends on whatever parameters you introduce, a, b, c, or whatever. So what do you have to do to find the lowest possible energy? What do you do in calculus to get the minimum of a function? Take the derivative, set the derivative equal to 0. So if we say derivative of guess energy with respect to a, that should be equal to 0. Okay? If you have more than one parameter, you can say the partial derivative of your guessed energy with respect to parameter b must be equal to 0, and so on. And if you did that, then you can find the best, lowest possible E. You're minimizing your guessed energy. Okay, so that's a variation method.